Here in AIT, the environment is truly international and multicultural, as people who work, study, and live here come from more than 30 countries across Asia and other continents. That's why I have plenty of chances to make new friends and learn about their cultures. The learning experience here in AIT helps students to achieve their full academic potential. The classes here have become a stage for students from different cultural and knowledge backgrounds to discuss issues that matter globally.
Being here, I was inspired by the Institute's goal of creating innovative solutions. My research focuses on novel green 3R biotechnology that recycles, reduces, and reuses our wastes. I am certain that the research findings we are doing here at AIT can potentially be applicable globally to make people's lives and environment better and to achieve sustainable development goals.
Social impact has been AIT's legacy and is still our positioning today. Social impact permeates our research and our education. We're injecting more innovation and multidisciplinary thinking in our research. We're engaging in more collaboration with globally prestigious universities, including dual degree programs. We're making AIT more relevant by broadening and deepening our network of businesses and NGOs and governments for the benefit of research, internship, and job placement. And we're nurturing entrepreneurship and service learning as part of AIT's experiential education.
A distinctive feature of our teaching and research programs is their close alignment with some of the major global challenges facing humanity. For example, climate change, energy, food, water security, technology, public policy mismatch, and human-machine fusion. Now, given the innate complexity of these challenges that defy straightforward explanations, our teaching and research programs emphasize multidisciplinarity, cross-thematic considerations, and pragmatic insights into the role of emerging technologies in broader socio-economic contexts.
We are working with many universities and governmental organizations in research collaboration and outreach activities. Some of our research findings have already been translated into new government regulations, new engineering standards and practice, and new engineering applications and tools. And I believe our long-term effort has created significant social and economic impact for communities in the region.
We believe that our main role is to produce experts who are truly global citizens who can think globally and act locally. Our School of Environment, Resource and Development takes an interdisciplinary approach to study, analyze, and solve global and regional sustainable development challenges, such as social and gender inequalities, rights and sustainability, urbanization and migration, food security, energy and environment, natural resources, and climate change.
The best management schools in the world are based on a strong industry involvement with leaders coming from around the world. It's also a place where a culture of innovation is encouraged. At our School of Management, that is the culture we're trying to encourage, with regular interaction with organizations and business schools where teaching staff and faculty come from around the world. No idea is discarded, and a multidisciplinary approach where collaboration with other schools is supported.
The Entrepreneurship Center is supporting AIT students, its faculty and alumni to transform their ideas into tangible outcomes such as prototypes, business plans, and startup companies. We aim to bring our experienced AIT alumni and successful entrepreneurs back to the campus to share their experience and stories, and to work with our students and faculty to build their dreams here at AIT.
It's not only the knowledge and subject in the classroom, but the way of thinking. Because when we come to work, it's not exactly as it happened in the books. So having AIT experience, so we look at this like a way of life, and I can find many solutions to overcome the obstacle, the problem. And also another thing is initiation. This is the very important thing for the success in the working life.
In my personal career, with the knowledge that I have gained from the Asian Institute of Technology, it has been very helpful in dealing with people, in managing my work life, in managing my family life, and also in actually furthering my knowledge through the research capacities that I have gained from the Asian Institute of Technology.
Graduates will be well prepared and have vast opportunities to pursue their passion for social impact by continuing in academia worldwide, or joining local or multinational companies, or working for socially focused NGOs, or becoming government officials, or starting their own businesses.
A very good afternoon from Remote Sensing and GIS AIT, and welcome to our fourth session of RSGIS Webinar Series 2. Today we have with us our recently PhD graduate, Dr. Zahid Wani. It feels great to call you Dr. Zahid. Welcome to our webinar series, and thank you so much for accepting to agreeing to share your expertise and research with us in this webinar series. You are also working currently at the Asia technology industry as a project quality and inspection manager. So before we go ahead with our so-called presentation, may I request you to tell us a little bit about your background and your current affiliation? Zahid.
Yeah, so thank you very much, Dr. Chitrini. Thank you for inviting me for the webinar, session 4. So currently I am Project Quality and Inspection Manager in Asia Technology Industry, which is a Japanese Thai company. So it has its office in Bangkok. So we work on autonomous driving, IoT related solutions, and some other works like navigation, indoor and outdoor navigation as well. So I have been working in GNSS for quite long now in that company. So we do, I have used BPP services, RTK and other things for autonomous driving. So I will share that some of the videos with you at the end.
Okay, and thank you so much. It's quite interesting for autonomous driving GNSS applications. Yeah. So can I request you to go ahead with the presentation, and then we will come with you some interaction questions and
yes,
about what you are doing.
Yes, sure.
During the session, our viewers, I want to request you, if you have some questions, please leave them in our comment box of Facebook or the chat box in our Zoom, so that we can handle them. Dr. Zahid will address them at the end of the session. Okay, Dr. Zahid, thank you.
Yeah, thank you. So is my screen visible?
Yes.
Yeah, okay, thank you very much. So today I will be talking about GNSS in urban areas where we require precise and reliable positioning. So firstly, what is GNSS? So many of you have heard about this term GNSS, but some may not. So in that case, they might have heard about GPS, which they use in mobile phones if they have to go from point 1 to point 2 or location 1 to location 2. So in that case, they use. So GPS is actually a navigation system, satellite system from USA. in addition to that, there are some other countries who have their global navigation satellite systems, which is GLONASS from Russia, then Galileo from European Union, then we have Baidu from China. So these 4 constellation of satellites, we call them as global navigation satellite systems. So the GPS chip that is inside the phone, it uses almost all these 4 constellations. That's why we call it as GNSS rather than calling it as GPS. In addition to these, we have some regional navigation satellite systems. One is IRNSS from India and QZSS from Japan. So these are called regional navigation satellite systems. In total, we have these as global navigation satellite system constellations. So the currently available number of satellites from each systems that we have is summarized in this table. And then these these satellites are at different orbits. So for Baidu and Galileo, even for IRNSS, they have at 3 to 2 different orbits, which is MEO, IGSO, and GEO orbits. Also, they provide different kind of services. So mostly all the satellite these constellations will provide the services about standard positioning services. They will provide, some of them provide the early warning services, then short messaging services, then precise point positioning services, and they are at different frequencies. So ranging from L1 to L5, then E1 for Galileo to E5A, E5B, and E6. However, Galileo and QZSS, they have an additional signal of E6 and L6, wherein they provide the precise positioning services which can be used for PPP directly from the satellites, which I will explain in the later slides. Then the steps that are involved in GNSS for the estimation of the positioning, velocity, and time, which is called PVT. First is the satellite, then we have the propagation of the signals from the satellite, then reception of those signals in the user segment, which is the device that the user will be using, and then the computation of those signals will be done so as to convert it into the PVT. Finally, that can be used as different applications. So in this case, we have 3 different segments or components, which is the space component, which is the satellite orbit and the satellite part. Next is the control component, wherein it monitors the health of the satellites, and it's distributed widely around the whole world. So we have master control stations, we have alternate master control stations, and there are some monitoring stations. Now, finally, we have the user component. The user component is wherein we can use the handheld GPS or the mobile phones or the smartwatches, or even the high-grade survey-grade receivers as well. So all these receivers that we'll be using, so it's important to know the performance of the GNSS. So in that case, the accuracy is very important. Then we have the integrity of the system along with the continuity. So it should be continuous, and also availability should be available in all weather conditions, whether it is rain or it's snow. So it should be available 24/7. So this is the current satellite status. If you see here in this picture, the number of satellites are more in Southeast Asia rather than other countries. And in this one, there is a lot of scope about GNSS, especially in Southeast Asian regions. However, if we use all these constellation of satellites, the minimum that we can receive in an open sky is more than 35 satellites at one time. Then we have the GNSS observables, which means we have 3 different kinds of observables from the GNSS. One is Doppler observable. Second is the pseudo-range observable, which mostly the mobile phones and handheld GNSS receivers use these kind of signals. And then we have carrier-based observables, which we need a dual frequency or even single frequency, wherein the raw measurement and carrier phase signal is being used to generate that. In this one, we can eliminate the tropospheric, ionospheric error, receiver hardware delays, and then multipath as well, and then satellite hardware delays that can be eliminated in this one. So this is the most precise one. If we are using, if we have to use, certainly for some precise application, we use carrier phase observables, including the pseudo range. So the errors that we get is broadly divided into 2. One is signal in space range error, another is user equipment error. So signal in space range error is actually the broadcast satellite orbit error, if there is some error in the orbit or the satellite clock or any other group delays. Then the user equipment error, it includes the ionospheric delay once the signal is being transmitted. So it has to pass through the ionosphere, the troposphere, and then in order to reach to the receiver. So these delays come into the UEE path and also the multipath, like if you are in a very harsh environment where there is high-rise buildings or in some forest area, so there will be multipath to the signal. So in this case, like when we combine these two errors, we get the user equipment range error. These all can be eliminated by using the carrier phase frequencies, wherein we can eliminate at least 2 millimeter level. Then we have the high accuracy observation methods. In that case, we have differential GPS, wherein we have also the real-time kinematic. Then we have precise point positioning. So in case of differential GPS, we use code phase observations or the pseudo range observations, and we require two different receivers. One will act as a base station, and another will act as a rover. So we need two receivers in order to do differential GPS. Same is the case with RTK. However, the difference between the RTK and differential GPS is only it uses code phase along with carrier phase observation, so it's more precise than differential GPS. Then we have PPP. In this PPP, it also uses code phase and carrier phase observations, but the correction data is being directly broadcasted from the satellite, so we do not need any base station. And with one receiver, we can do PPP. So the accuracy of these different methods like differential GNSS or SPAS, RTK, and PPP, it varies. So the baseline is very important in case of RTK and differential GNSS, wherein the reference station, it varies. Like as you increase the distance between the rover and the reference, the accuracy will degrade. However, for PPP and SPAS, it will be same because it's being broadcasted from the satellite. It only depends upon how the reception of the satellites and where your receiver is. Then there are different receivers that are available in the market. Firstly, many of you might have used the handheld GPS receiver or GNSS receivers, or it is inbuilt in the watches or in mobile phones, whether it's iOS, Android, or Windows. So these are called handheld receivers, which use standard GNSS only. Then we have some low-cost receivers, wherein you can use raw data and you can process that one using base station, or you can use that process through RTK or PPP or even differential GNSS. In this one, these are very low cost. These are just $20 receivers with L1 frequency only. Then in addition to this one, uBlocks has also launched some other low cost receivers, which are like $100 receivers. Like they have we call them as dual frequency receivers. So here you can get more precise and reliable results than from the single frequency receivers. In addition to that, we also have survey grade receivers, which are very accurate, and they provide you millimeter accuracy in terms of open sky measurements. So these are expensive, and we call them as survey grade receivers. So my research was to generate the digital elevation model for urban areas using GNSS. So for that one, let me first explain what DEM is. So in DEM, each term has its own diverse interpretation, where D refers to the digital or can be a triangulated irregular network. It can be digital line graphs, grids, or point clouds from the LiDAR. And E here refers to the elevation in state of nature without building and vegetation, whereas M is the modeling part in the DEM and has not received much attention. Indeed, as we know that DEM is the representation of the landscape. However, the challenge is to construct this DEM for the known and inferred properties. DEM has to be broad and comprehensive in a spatial scope. Significant efforts have already been made in recent times to design and develop highly accurate digital elevation model generation techniques. But the objective, scope, location, and budget will define which of these methods are appropriate. So in case of urban DEM, it's very, very important. The need of the construction of the urban DEM is increasing in importance across the world, because there are many applications, especially that we use. Some of them which I have summarized here is like special analysis of GIS, urban planning, management, development, and monitoring, and also about urban climate studies. And we have visualization of urban landscape. We have analysis of terrain visibility, renewable energy studies, road planning and construction, and also nowadays we use for autonomous driving. These are the applications that are for the positioning only, but there are some applications related to timing as well, because it provides you very precise timing. So in It also aids to the high integrity of global positioning system pseudo range measurements, which I already mentioned. Like if we are using handheld receivers, then we use pseudo range measurements. So it will provide high integrity to those kind of methods if we are using, especially in environments with urban canyon. Therefore, the availability of global, consistent, and high quality DEMs is very vital. So based on that, like the currently available DEMs I have categorized in my research. So let me first tell about the in association with DEM, there are certain terms which are used. Those are DTM and DSM. So the digital terrain model is the bare earth surface where from the elevation is being collected. However, in DSM it can include the buildings as well as trees or any other feature, man-made or natural, that is present on the earth's surface. So it includes all the elevation data from those features as well. So in terms of DEM, so I have categorized in my research into three main three categorizations. One is the coverage, then its data structure, and then its technology, how we are generating the DEM. So in terms of coverage, firstly it will be global DEM, then it will be national, or it can be a local or regional DEMs. So in terms of the data structure, it can be a raster or in TIN form. And in terms of technology, it can be geodetic, wherein we can collect the data using traditional survey method or total stations we can use. Then we have the radar, SAR, or LiDAR based DEMs, and also photogrammetric based DEMs, wherein from different aerial photographs or satellite images, we can generate the DEM from the stereo peer images of those. Then why GNSS in urban areas? Firstly, there are no precise available DEM. The DEMs are available and they have an accuracy of up to 1 meter. But however, in some very precise applications like flood simulations or disaster events, we need more accurately DEM for urban areas. Secondly, it's very difficult to generate the DEM in urban areas from space-bound platforms, like because there are many types of occlusions and also urban canyon which block the sensors to capture the data. Also, airborne platforms, we can use this one and they are very accurate. However, they are very costly as well. And frequently flying those kind of airborne platform, using airborne platforms is not feasible because of the areas where it has cloud and fog. So it becomes problematic. Then we have ground survey, where we use total stations in order to collect the elevation data. It's very much odious. High cost is required. Human error is much into those, and also it's very difficult to survey periodically if we have to update our systems like every year. So it's very difficult in that way. Also, the urban areas are changing continuously, and there is like increase in areas. There are no new roads which are being constructed, and so many other things. So we need to update the DEMS precisely. So in addition to this, there are mobile mapping services also, but they are integrated. They contain the systematic errors in data acquisition, and there is no inherent redundancy into those. So based on this, we have used GNSS as it provides you the positioning, the latitude, longitude, and the height. However, in this case, GNSS does not provide orthometric height, which is being used mainly for the engineering works. So it provides you ellipsoidal heights. In order to generate the orthometric height from the ellipsoidal heights, we use a geoid. So these are the undulations on the Earth's surface. They are like global geoid models available, and also many developed countries have their own geoid models, which are very much precise. So in this case, the orthometric height is generated from the ellipsoidal height when we make the difference from the geoid undulations. So we get the orthometric height or the mean sea level height. Then in order to generate the DIM in my study area, which was in Bangkok, we have to first plan how we will collect the data based on that one, then how which platform we will be using and other information. So in this case, we have chosen firstly the reference station, which was Chulalongkorn University reference station. Then we have done the survey on different days in order to cover more area. And then after that we have processed. So in case of processing, it can be real time or it can be post processing. So in our method we have choose post processing method, and then we have merged all those data sets using spatial merging techniques, and then to make a full data set. After that, there are many wrong fixes in the PPK data. So to eliminate those wrong fixed solutions, we have used sort of statistical methods to do that. Also, we have to remove, as I previously mentioned, that for the DEM, it is only the bare earth data. So there are sometimes the overpasses or the flyovers or the U-turn bridges are there, which we have to eliminate from our data set in order to generate the precise DEM. So for that one, we have developed an algorithm which removes all those regions or the point data from particularly which does not represent the elevation data for generation of the DEM. And then finally we generate the DEM. In order to check the accuracy assessment, we have used Bank of Metropolitan control points from the department, and also from the Royal Thai Survey Department. We have used the control points from them. Also, wherever there were not availability of those control points, we have used the field visits where we have collected manually the data for like 30 minutes and then process that and use that as to validate our DEM. Then in this case, first, as I mentioned, was to design the framework for positioning and processing of multi-GNSS data. So in that one, first it was planning and reconnaissance. So we have to look for the sky plots and the dope values in our desired route wherever we have to collect the data. So for that one, after that, we have to decide which positioning method we will be using, whether it will be a kinematic or it will be a stop and go method. And finally, by which process we will process our data, whether it's an RTK or it's a PPP method. So based on that one, then after we collect the data, so in this case, like how we have chosen the reference station, which was Chulalongkorn University reference station, and then we have used the rover, which was installed on the van. So in this case, for PPP or RTK, we can use both. Only the difference between the two is, one, for RTK, we use the data connection wherein the correction data will be sent from the reference station to the rover in real time. And in post-processing, we can collect the data from both reference station as well as from the rover, and later on we can process them. So these, in my research, I have used is the PPK method, which is post-processing kinematic method. So in this case, these are different models that I have used in order to eliminate the different kind of errors that is being induced. So positioning mode was carrier phase kinematic positioning. Then the constellations I have used was all the global positioning systems, and also the global navigation satellite systems, and also the regional navigation satellite systems. However, we could not access the IRNSS, so we have just used the QCSS. And the cutoff elevation mask angle for us, we have chosen 15 degree. We have tested it for different mask angles, but 15 degree gave us better results. And for us, the sampling rate was 1 Hertz. The ionospheric correction data was processed through the broadcast ionospheric model. For tropospheric correction, we have used a Sestamonium model. And for satellite ephemeris and clock, we have used broadcast ephemeris. Then the integer, in order to resolve the integer ambiguity, that is the N, we have used the continuous method, which is in RTK-lib software. In that one, it resolves and estimates the integer ambiguity continuously. And then the minimum ratio to fix ambiguity, which is a ratio test in order to choose how much integer ambiguity has been resolved. So we have set up at 3, and we have used actually different values for this one. 3 gave us better results. And then finally the recording method. So for base station, it was on the rooftop of it was at static, and it was installed on the rooftop. And for kinematic one, we have installed it on the vehicle, which we have driven through the Bangkok roads. Then I also mentioned, like, we have to remove the wrong fixed solutions, which will be from the processing when we do processing, post-processing, or even in real-time processing. So there are some wrong fixed solutions which we have to remove. In this case, we have used simple descriptive statistics and the outlier filtering algorithms available. So in that one, we have applied MAD-E, Pearson's method, in which there is Z score and modified Z score, and interquartile methods. all these methods have detected those wrong fixed solutions, and then we have validated those solutions through field visits, and also we have captured the videos on when we had done the experiments to know whether these are really the wrong fixed solutions or and there is some other issues. So after we have removed the wrong fixed solutions, then we have to remove the data from the overhead bridges, overpasses, or the U-turn bridges in case of urban Bangkok. So in this case, we have developed an algorithm that is spatial outlier filtering algorithm. In this, we need 4 different inputs. One, we need the X, which is the spatial data, which is latitude and longitude. Second, we need non-spatial attribute data, which can be elevation or any other kind of data the user is collecting. And then they should also determine the number of neighbors that for clustering purpose. And finally, the threshold limit has to be decided. And then it will give us the output, which will detect the point as well as the regions in particularly for the overpasses. So this is how we have generated. So we have used cluster size, different cluster sizes, and then based on that one, then it calculates difference between the elevation. So it's a one-dimensional algorithm wherein it will calculate, it will first cluster based on X, then it will use for threshold in order to eliminate those, it will use the non-spatial attribute data that can be anything. In our case, it was height. So finally, we get the output from this. So it's the spatial outlier filtering algorithm that we have developed is based on a graph-based algorithm. So finally, for users, we have developed an interpolation service wherein there are 3 different domains. One is visualization domain, another is filtering domain, and finally it's interpolation domain. So it was developed in order because the softwares are expensive and then no one wants to go deep into the programming, and also for those disaster events or such wherein they can use this kind of a program. It's available online. So in this one, the visualization domain is first they will upload their own data sets, and it should be in CSV or any other text format, and they will the software will automatically ask them where is the latitude into that particular file, latitude, longitude, and the elevation data into that particular file. Then after it's being provided the drop down disk they can upload, and then finally it will be visualized as a GeoJSON format on the web map. And the descriptive statistics along with the particular non-attribute field, the graphs will be plotted. So if there is a need of filtering, so they can use the filtering algorithm, wherein they have to input only the threshold and the filtering size for that. And for threshold, we have like used the different like they can visualize which is best suitable threshold for them. Based on that, they can use that threshold and they can continue to interpolate their data. So currently we have only the deterministic interpolation method available in our system, which is like but it gives you 3 interpolation techniques, whether it's linear, cubic, or nearest neighborhood. Also, there are some additional functionalities that are being provided where the user can add the cell size, and then he can download this particular interpolated layer as a GeoTIFF format. So in future, we may be adding more interpolation methods like the statistical interpolation methods. So these were the platforms that we have used. So for Bangkok, we have used the WAN. We have installed the receivers on top, on the antennas on top of the vehicle. And we have also used a simple platform for testing whether we should use stop and go or we should use the kinematic method for data collection. So in that case, we have also used bicycle inside AIT only. So the experiment that we have done, the experimental area that was surveyed was around 90 kilometers. The baseline, the distance between the rover and the reference station was 13.3 kilometers. Sampling rate, as I mentioned, it was 1 second. Mask angle was 15 degrees. Positioning method was kinematic, and processing method was PPK. So in this case, like we have 2 different receivers. One was NetR9, which uses almost all the constellations except IRNSS. And then Sigma was Javad receiver, which use only GPS and GLONASS. So here you can see the difference in terms of fix rate. So in case of NetR9, we get 71.92%. However, in case of Sigma, which is from Javad, we get only 28.06%. So this shows the difference between if you use all the constellations, multi-GNSS constellations, rather than using just two constellations. Then these are the number of satellites and the CUT reference station that was in our study area. And this is from the Trimble Network 9 receiver. So minimum was four number of satellites that we have received, and the maximum was 17. Then the wrong fixed solutions that we had to eliminate. So in this case, these are the results from all those four techniques, statistical methods that we have used, like Z-score, MZI, modified Z-score, then MAD-E and IQR. So in this case, we can see like the green is the two epochs, and then the wrong fixed by MZI is detected by blue, and wrong fixes by Z-score is detected by red. So modified Z-score detected very precisely the wrong fixed solutions. Then third was the SOFA algorithm that we have developed to eliminate the data from the overpasses. So in this one, in our study area, there were 35 regions detected by SOFA. And in those, 24 were bridges and 2 were flyovers. 3 regions were the cross-section of the roads, wherein there was railway crossing and the other roadways. And one region, in that one region was like railway track and road. So we have used the precise recall and accuracy in order to determine the accuracy of the algorithm. So 74.29% was precision of our algorithm so far. Then 100% was the recall rate, and then 99.92% was the accuracy of that particular algorithm. So let me show you the bridges that we have detected in the study area. So it's quite precisely detecting those regions rather than not to eliminate other things. So it detects point as well as regions in data filtering. Then these are the results of the data, the DEMs that is generated for AIT and also for the Bangkok. In addition to these, we also have collected data from Jakarta, Philippines, and also we have used taxi probe data for Bangkok metropolitan area. So in that one, these are the DEMs generated. Also, our plan was to use to install the low-cost GNSS receivers in taxis or in any other public transport, so that they will collect the data automatically, and we can receive that data and we can process that data later on for post-processing, and then we can generate the precise time. So we can get continuous data based on this. So this makes our system very low cost for DEM generation, and also very much reliable and precise. So then we have also done the accuracy assessment of the DEM. As I mentioned, we have used the ground control points, and also as the points, some of the points that we have collected by field visits. So in this case, we have divided our study area into 2 parts. One is the data collected from on-road data, which is from the roads, and another one we have collected for off-road data, where the vehicle cannot go, where we have manually collected the data. So in that case, the on-road were very precise because we had more number of data sets from that particular area. So it was 0.15 meter. For off-road, it was 0.66 meter, the bias. And the overall, it was 0.24 meter bias. Then also we had installed some carbon dioxide sensors into that particular experimental areas. So this is the interpolated layer, and we have used, in this case also, we have used the SOFA algorithm in order to check the how it will behave when different kind of data sets are being used, not only elevation, but some carbon dioxide or some other kind of data, non-spatial data which is being in the attribute table. So it was also very precise. So this was all about in my PhD what I have done in AIT, and that's it.
Thank you, Dr. Zahid, for such a comprehensive talk, because you not only shared your research, but also talked a lot about like how GNSS can be used in urban areas also. We have a quick question in Zoom, so we ask that first, and then we'll go ahead for the rest of the part. what was the spatial resolution of the DEM?
So it was 10 centimeter.
All right. So I'm actually curious about like your even current work, your in ATI, the Asia Technology Industry. Yeah. So can you share a little bit more, if it is permitted, like what's your work in like autonomous vehicles in GNSS?
Yeah, it's okay. I can share that one as well. Let me share the screen. So the GNSS is autonomous driving. That one is what currently I'm working on. So in this one, we have like the automated driving and the target performance. Like we know that in luxurious cars, which go on a high speed of around 100 kilometers, and then it can be affordable to only rich people, and then it can also go for long drive. But in this case, we have the low cost autonomous driving system developed, wherein we use small EV vehicles, we modify them and make them into autonomous ones. So the maximum speed for those vehicles is 40 kilometers, wherein they can be used by the old people. Then also those who need help, they can book and then they can use those kind of vehicles. And it can be used for short distances as well. Then however, in highways it cannot be used, but for live roads it can be used. Also for mixed roads it can be used. If it's dedicated lanes, it can be used for dedicated lanes as well. Then it can be used in case of snow or in case of rain. So this was developed for Japan, wherein it has snow, but in Thailand we don't have. So so these are the things that our system can give for the low cost, like for using the EV cars. And the project service area, that was like because for Japan mostly there are some areas which are depopulated and there are only old people living. So in order to go to the necessary facilities of the life, like supermarkets or government offices, community centers, railway, hospitals, or any other clinics, so they need to visit. For that one, we provide the services which using the autonomous EV vehicles. And then they are also like, if in case the autonomous system there's a breakdown, so it's also monitored from the vehicle remote control and can be controlled through our staff as well. And for charging, we have the auto sharing charge parkings in Japan, and wherein we use solar power to power all those. So in this case, like how it works, that's more important. Like first is vehicle position recognition. So we need to know where the vehicle is. So for that one, we use GNSS. So we have used the RTK as well as PPP methods for this one. So this one I'm showing for the Maduka PPP, in which we don't need any base station. We get the direct correction data from the satellite. So we use the QZSS, which is Maduka PPP from Japan. Then after we recognize the vehicle position, we also should know about the external, what are outside the vehicle. So for that one, we use different camera systems. We use the LiDAR rangefinder, and we use side millimeter radar to detect the outside environment of the vehicle. And then finally, we have to there is action plan, wherein we use both vehicle positioning and external recognition. And then there are some deep learning algorithms involved in it, wherein it will automatically plan the trajectory. If we have to change the course, then lane changing or something related to that, so it will do that one as well. So we use 3 different kind of ECU boards. One is for auto acceleration, and then another is for braking system, and another one is for this auto steering. So in this case, it's very low cost because we don't use high-end receivers. We use very low. We use U-Blocks receivers for this one, which are like $100 receivers. However, there's a different way how we do things. We use dual antenna system receivers in this case. So we have also demonstrated in SKP and Gista. This was our track where we have to demonstrate the autonomous driving, and it was like it can do it can work very fine in open areas as well as in harsh environments, or wherein GNSS receiver cannot receive the signal directly, wherein there is a lot of multipath available. So also we have tested for the Chulalongkorn University. So here we have used F9P receivers, and the results were very good. Even in this one, we can see from the images how harsh the environment is for the GNSS reception. Then live monitoring was our other main target, like if in case there's a breakdown in the system, so how we can monitor it from our control room. So we use two different kind of cameras. One we use for the external view, another we use for the internal view. So then it goes to the cloud to our server, and then where we can visualize the environment outside and inside of the vehicle as well. Then this is a small video which I want to show. So this is all autonomous driving. So there's no one inside the car, it's autonomously driving. So this is the external view that I was telling, like to recognize the external environment, and also the internal one. So here we use two antenna system. The front one is the positioning, and back one, the back is the positioning, front where we provide the vector. We use heading in order to be on the path. So then this was just a video, and this is the explanation of that particular video, which is available on YouTube as well. So I will just skip this one, and if you want to visit our company website, you can find all these informations over there. So this is the company website, www.agi.com.
So you can just share the video link, so we can just put in the Facebook Live page.
Okay, I will share it in Zoom.
Yeah.
So, okay.
Yeah. You mentioned about you used PPP for this purpose, right?
Yeah.
GNSS. Yeah. So what are other types, and like why PPP, and like how do you decide? Like
because there are some areas.
Yeah.
Yeah, there are some areas wherein base stations are not available. So if we increase the distance between the rover and the base station, the accuracy will decrease. So in order to eliminate that thing, so we use directly the correction data broadcasted from the satellite. It will be more precise in case of Japan, because we use the Japan regional navigation satellite system. However, that can be used in Thailand, but in other countries we cannot use that. It can be used in Southeast Asia. So that's the reason why we use the PPP rather than RTK.
Okay, so let's go ahead with some questions that we have. What are the challenges in GNSS research that maybe you face or you know from other literature surveys and all?
So mostly it is like if you talk about urban areas, the challenge is to eliminate the errors. So to collect the data, and then also like in traffics, you are stuck there for quite long. So you have to eliminate those things as well. And currently, if we talk about the Southeast Asia, as I show in one of the slides, the number of satellites that are available is more than 35. So in that case, it's very good if we use all the constellations available, whether it's regional or it's global. If we are using just two constellations, GPS and GLONASS, then it might not give you that results that are required for your project.
Okay, and you use some specifics. What you call this is like receivers for the GNSS, right? Like, how do you decide like what kind of receivers? I mean, how do you choose the receiver?
So it depends upon what accuracy your project requires. If you require very precise accuracy, then it's very important to use survey grade receivers, which has like not dual but triple frequency receivers, and using all constellations, and even as BAS and other satellite based augmented systems as well. So if we have to use like 10 meter or something, so we can use some low cost receivers. We don't need to use the survey grade receivers, which are very expensive to use. So it depends upon application, which application we are using, and then the budget as well.
Then we have one question for your this autonomous vehicle. Do you need a specific lane for the autonomous vehicle?
No, currently we don't need, because like we are tracing it on the road. We are just driving once on the road, so we are tracing that line then. So in that case, if there is some vehicle or there is some blockage inside in front of the vehicle, so vehicle will automatically change its lane and come back to that lane again.
Okay, so that's the answer for the question asked in Zoom. Then say, for example, like someone is like some new student is starting to work on GNSS. So what is your advice to start with? Like what kind of tools or techniques they should learn with, like, to start with GNSS research?
So it also depends upon which project they are working on. If they are working
like, for
on
example, urban areas and
so
them creation, yeah.
Yeah, so for urban areas, and then what in that project, what should be the accuracy they have to attain. So if they have to attain like very precise, like centimeter level accuracy, then it's better to go for the survey grade receivers with multi GNSS constellation support, not only GPS and GLONASS. And then they can, like for usually there are two techniques. One, it can be done in real time, and one, it can be done in post-processing. So if their project is like they can post-process it and use, then it's better to use post-processing method, wherein they have the data, raw data, and they can analyze different kind of available algorithms for different eliminating different errors. And so it's very important. Otherwise, if they use RTK and then their project does not require RTK, but they just process it, so it's one time, then they cannot use that data again. So it's better to use PPK, which is post-processing kinematic, for those kind of research. And there are also many softwares available, freely available softwares or open source softwares like RTKlib, which is very easy to use. They have the manual, so they can use that.
Okay. So it's a like graphical user interface kind of software.
Yes,
where students can use. Okay.
Yeah.
Good to know. Then we have one question, like, can we have the recording of the sessions and also previous sessions? So I will answer that. We all, like all the recordings are in the web page already. So you can search in the videos. So you can look for this video or our previous videos as well. And so we are sharing now from Dr. Zahid the link for the YouTube video, what he was mentioning. So you can have a look if you have further interest to view the video. So one last question, if we don't have any question from our Zoom participant and Facebook, let me check once again. Okay, they're done. I think all questions are handled, addressed. So one last question, and it's a general question. So since you are very like recently PhD graduate, any piece of advice for our PhD students or any other PhD students who are starting or continuing PhD research, like what do you advise them? How to go ahead with the research? Because you need a lot of patience and like things, whatever topic is, yeah.
Yeah, so whatever the topic is, patience is required. And in addition to that, it's better if we are very clear-headed about our proposal, what we are going to do. So if we are clear into that one, then it will not take that long.
Okay, and what about like publications? Like, what is your advice for publications?
If they have budget in their project, just go for open access ones, because it takes long for the other journals to publish, and then it's a requirement. So we can publish papers later on in very reputed journals, but for the sake of graduation, so like the requirement is one. So if we can get better than one impact factor journal, it's good enough. So it will not waste our long time. Because reputed journals are like where you have to wait quite long, and then there are so many reviewers, you have to reply to them.
Yeah, we still have questions coming, so we can take this. I think we have still time. The autonomous vehicle can recognize traffic lights?
Yeah, it can.
It can.
Yeah, it can.
Like, is there a sensor, or how does it do
cameras are there, so it will, based on that, it will detect.
Okay, is there a distance, like how long?
Yeah, we can, yes, we can. It's up to us how far we want to recognize the traffic lights and all.
Okay.
So we can program that.
Yeah. So we actually have very interesting talk today from Dr. Zahid. Not only his research, but his current work in ATI. It's very interesting how GNSS is working, using in, getting used in autonomous vehicles, which is like currently very popular. Okay, thank you so much, Dr. Zahid, for being with us today, despite your COVID situations. Like, we know, like, you have suffered a long time. Even you had to give your final defense when you were positive. So good luck with you, like for your future endeavor, whatever you do. All our wishes are with you. And thank you so much for being with us today. And thank you so much for our viewers for being with us today. And for the next session, we will be posting the information very soon. And for today, we thank you all and see you again, hopefully, in the coming weeks. Thank you.